Today we are going to discuss one of the most difficult challenges in the iron making, seeing what's happening inside the blast furnace hearth. For decades, the hearth has been a black box where we relied on the guesswork to manage molten metal and slag level. My goal today is to provide you with a practical guide to installing and reading EMF sensors. So we will start with the core physics, move through a detailed installation journey and finish by showing you how to turn raw electrical signal into precise operational decision. So by end of this session, you will understand how to use this electronic eye to improve safety and efficiency in your daily operation. But first, let's look at why operating without this data is so risky. Now, look at the screen. On the left, we see the reality of the cast house massive steel mount structure. On the right, the physics panel shows what's actually happening inside a turbulent molten pool at over 1500 Celsius under immense pressure. So the risk here is invisible. If molten slag and iron rise too high, they can disrupt gas flow, number one, damage the refractory lining, or even flood the tuyer, which can lead to a catastrophic shutdown. And it's altogether not safe. Our goal is to track the exact level of these liquids in real time without ever opening the furnace or stopping the furnace. So we have tried solving this with different tools over the years. So let's look at how the technology has evolved. Now, you please go through this chart, and as you can see, this right from sounding board to strain gauges, were already tried right from beginning, but the strain gauges up to certain extent has given a good support. Uh, but as far the accuracy level is concerned, that were not pretty good. We can say it's low accuracy, intermittent, and dangerous for operators. So, as for the strain gases as concerned, they measure the physical bulge of the shell under the pressure. It's safer, but they cannot tell the difference between metal and slag. How look at the green column EMF and resistance sensors. They provide continuous millimeter accurate data with zero operator exposure. Now this is the future of the casters management. To use this system, we first need to understand the physics, how the furnace generates its own signal, because this is the fundamental that we must have to learn first. Now the furnace is a giant battery. Think of the blast furnace heart as a massive car battery. Inside we have a coke acting as an anode, molten iron as a cathode, and slag as electrolyte. So this setup naturally generates its own electrical voltage, what we call EMF, electromotive force. So as the level of the hot metal rises and hits the carbon wall, this voltage signature changes. Now by measuring this teeny millivolt fluctuation on the outside steel cell, we can calculate exactly how much liquid is accumulating inside. While that's the passive signal, we also have an active method to get even cleaner data. Now beyond the battery effect, we can treat the heart as a giant resistor. In the ITU approach, also known as 4-point probing, we send a teeny safe electrical pulse through the furnace shell. Here is the key. Molten iron is a fantastic conductor. It's like a copper wire. Slag, however, is an insulator, more like a rubber coating. As the iron level rises, it shorts the internal electrical path and the overall resistance drop. This allows the system to draw a perfect line between the iron and slag. Now that we know how it works. So let's walk through the actual installation on a 10,000 ton per day furnace. Now this is the hardware roadmap. It's a four-stage process: sensors, junction box, wiring bridge, and finally the control room. So for a furnace of this capacity, we cannot rely on just one sensor. We installed multiple sensor array around the entire circumference to detect if liquids are pooling unevenly, perhaps due to blocked deadband also. And this is a good way to also measure that sort of a deadband configuration in the furnace. Whether this deadband's exactly in the center or symmetrical, this is also we can able to find out from the electrical signals. So let's see the step one, or choosing where and how to place the sensors. So coming to the step one, uh, about which is about step one. Uh, so you have a two primary options here. So cell welded probes are the non-invasible choice. We weld low carbon steel walls directly to the outer shell. Okay, so they are easy to maintain and would not cause the gas leak. Now refractory embedded probes gets closer to the molten liquid for a stronger signal, but they are much harder to install and can fail as the brick expand. So for your installation, we recommend shell welded probes placed at a specific elevation, typically just below the tuer and at hearth floor level, to capture the full liquid range. Once the sensors are mounted, we have to protect that delicate signal. Now the raw signal from the shell is tiny. We are talking about about the microvolts. So in the noisy environment of the cast house, that signal could easily be lost. So that's why we use heavy duty shielded compensation wires to run the data across a delicate wiring bridge. Now this protected from the magnetic interference from big motors and machinery. Finally, the signal reaches a converter in a temperature controlled cabinet. This is where the magic happens. We use an extended Kalman filter to clean the electrical noise and translate those raw voltage into readable level data. Now let's see what's the operator actually see on the screen. This is the operator's cockpit. Inside of millivolt, the software shows a 3D mapping of the hearth. Because we have a sensors all around the circumference, the screen can show if liquids are pooling unevenly. For example, look at the red area. Look at the red area in the center. That's the block dead man. Altering the operators, that flow is restricted. So this real-time action allows the team to watch the hearth fill and drain like they are looking through a window. So to use this effectively, you need to recognize the three distinct pulses of the tapping cycle, and which are very important. So as the slide, it's showing that the between cast, when the tap hole is plugged, we see the pulse filling. Notice the steady continuous upward climb in the signal. Inside the furnace, molten iron and slag are accumulating in the wards of the cook bed. As an operator, your job is to monitor the steepness of the climb, of this climb. So the system uses this to predict exactly when the critical safe limit, usually 50% occupancy, will be reached, giving you a precise countdown to drill the tap hole. Now what happens when you actually start the tap? So when the tap will open, the signal drop rapidly, and this is phase 1, the iron flow. So notice this distinct kink or gradient change. So that tells the keeper exactly when the lighter insulating slag has reached the tap hole. If the signal gradient is lower than the usual, it's a warning that the tap hole might be choked by the blockages or not siphoning from the right point, or any short circuiting, and you might need to redrill, close and redrill, or other philosophy what is being exercised in that shop on that top floor. So this helps us manage slag separation with the pinpoint accuracy. Eventually this signal will level off, which brings us to the most critical decision point. Now this is the pulse, the dry hearth, where this signal hits a minimum plateau and stop dropping. This is saturation. This saturation point is the definitive signal that the liquid level has already taken into action, as it is already shown here. So this is the optimum time to swing the mud gun and plug the tap hole. It prevents the hot gases from escaping and reduces unnecessary wear on the tap hole refractory, which is a very detrimental for the furnace campaign. But the benefit of this system go beyond just liquid level. We can also track the hearth of the furnace. Now we can also use EMF magnitude to uh, uh, evaluate, to monitor the refractive erosion. There is an empirical relationship. As the wall gets thinner, the electrical resistance drop and the EMF magnitude increases. For example, if our baseline signal shift from 5.3 to 8.2 millivolt at the same temperature, you can estimate that about 95 milliampere of refractory have been lost. So additionally, the uh, uh, Nernst equation allows to relate these voltages to oxygen activity, also giving us a chemical thermometer to protect the silicon content of hot metal before it even leaves the furnace. So let's bring it all together, and once we bring it all together, uh, we start like something this slide shows. We started today with a black box, but we are now ending with a connected cast house. By combining continuous sensing hardware with the predictive data intelligence, we empower operator to make proactive data driven decisions. Remember the three takeaways. That is, the redundancy is the key. Always use multiple sensors to map the hearth in 3D. Read the signatures, use the tapping signals and saturation points to optimize our cast. Monitor the baseline, use EMF magnitude to track refractive wear and the thermal health. So, by turning complex electrical physics into simple, actionable visual, we make the blast furnace operation safer, smarter, and much more efficient.